Chapter 1, Algebraic Methods, Section 1.1, Proof by Contradiction. So what is proof by contradiction? You are going to assume that the statement that you are trying to prove is not true. It's called negation of the statement that you are trying to prove. And through the logical process, you're going to arrive at an impossible result. So it could be a contradiction of what you are proving, so contradiction of your assumption, or of some other fact that it's known to be true. So in the example 1, we're going to prove by contradiction that there is no greatest odd integer. So we're going to begin by making an assumption. So my assumption is there is a greatest odd integer. Okay, that let's call that integer n. If there is a greatest odd integer n, then what will happen if I consider n plus 2? So this is an odd integer plus 2. This will also an odd integer, because you've got odd plus 2, which is even, results with an odd number. Also, n plus 2 is greater than n. So greater and odd. Therefore, by contradiction, the assumption is not true, so there is no greatest odd integer. So I've got an assumption. We are going to consider an integer that's also possibly odd, that's greater than n. You could have used n plus 4 if you wanted to. It's definitely bigger than n, and it's definitely an odd number. Therefore, by contradiction, we have proven that there is no greatest odd integer. So going on to example 2, we've got to prove by contradiction that if n squared is even, then n must be even. So our assumption in this statement is going to there exists a number n such that n squared is even, however n is odd. So we are going to contradict this statement. So in that case, we're going to begin by writing our n as an odd number. So if n is odd, then I can write n as a usual standard way of writing an odd number is 2k plus 1. K belongs to z numbers, that's an integer. So if n is definitely odd, what happens if I consider n squared? So then n squared is going to be 2k plus 1 all squared. That gives me 4k squared plus 4k plus 1 if I expand it. Now clearly I can write it as 2 lots of 2k squared plus 2k and then plus 1. So this is even plus odd. It is in that standard form of an odd number, so therefore that is an odd number. Okay, so this is a contradiction of the assumption Therefore, if n squared is even, then n must be even also. Okay, so before we move on to example 3, let's just remind ourselves from lower down the school what a rational number is. So you may not remember that it's rational numbers, set of rational numbers is written as Q, a funny Q there. And you also have a set of irrational numbers. So rational number is any number that can be written as a fraction, A over B. So any whole number, so for example 2, can be written as 2 over 1. That's a rational number. Now an irrational number is the one that cannot be written as a fraction. So for example pi, or pi squared, or root 2, or root 2 plus 20. You also know ln2. That's another irrational number. So something that cannot be written as a fraction. So very often in proofs you've got, they really seem to like this proof. And you use the proof by contradiction. So I suggest practicing this proof a few times. It can be adapted for root 3. So we're going to prove that root 2 is an irrational number. And we're going to make an assumption. So our assumption is going to be root 2 is a rational number. So what does it mean? So if it is, then root 2 can be written as a fraction. Let's put A over B. But in its lowest terms, meaning there is no common factor between A and B other than 1. So it's been cancelled down into its lowest terms. So what are we going to do? We are going to, like I said, practice that a few times. The first thing we're going to do, we're going to square both sides, because if root 2 is A over B, then 2 is going to be A squared over B squared. But then if you rearrange it, you will have A squared is equal to 2B squared. So what does it mean? That means that A squared must be even. So A squared is an even number. Because clearly we have got, it's written as a multiple of 2. So if A squared is an even number, then it means that A must also be even. So let A be equal to 2m. So that means A squared must be equal to 4m squared. So if I now replace this with 4m squared, cancel by 2, you will have B squared is 2m squared, which means that B squared is also even. So B must be even. Now what does it mean? It means that if both A and B are even, then they must have common factor of 2. And this contradicts. This is a contradiction of the fact that both A and B have no common factors. It seems to be a lot of writing, but you're better off writing more than there's our assumption here than not. And then you have to write down the conclusion. So in the conclusion, therefore, we use the word contradiction, by proof of contradiction, root 2 is an irrational number. So we started here with our assumption, then we follow the steps over here. So our assumption is all the way up to there, and then we started deriving, like writing our well, still part 2 as logical steps, and this is our conclusions, but this is the second part, so it follows those steps. Good, so we're going to just have a look at next example, which is the last example before you have a go at exercise 1A. It's proof by contradiction that there are infinitely many prime numbers. This is another proof that I would strongly suggest you practice writing it out in case you get it asked. It's a very, very famous proof, so please learn how it works and why it works. So assumption here is there is a finite number of prime numbers. That means there's that amount of prime numbers, there's no more to be found. So if we're going to assume that all our prime numbers, so let all primes be P1 for prime, P2, P3, and let's say Pn. So there are n primes. Now then consider, so think about this number. Number that's made out of P1 times P2 times P3 times all the prime numbers all the way up to Pn, and then add 1 to it. So now if you divide that number, whatever we call it, let's call it number P, why not, by any of the prime numbers, then you will always get a remainder 1. So think about it. This is, you don't have this, so you can divide it by P1 and you will get all the other primes numbers multiplied together. You will always have the remainder 1. So if you divide P by any of the n primes, you obtain the remainder 1. Okay, so a remainder 1. So none of the prime numbers is a factor of that. So none of P1 all the way up to Pn is a factor of P. So what does it mean? It means there must be another, at least one prime number that will divide P. So it will divide P, so is a factor of P. So either P is completely new prime, maybe not new, is a prime number, or another prime number is a factor of P. What does it mean? It means, this means that P1, P2, all the way out to Pn is not a complete set of all prime numbers or possible prime numbers. So it's a contradiction of the assumption therefore there is an infinite number of prime numbers. So it seems like a lot of writing again. This is the most you write in maths, but it's very important proof. Please memorize it, learn it, don't forget any steps. So have a go at exercise 1A. Do it really carefully. As soon as you've done the first question or even part A, check with the back of the book, because it's just like a learning curve. It's a completely new way of proving mathematical statements. Good.